Hi everyone, my name is Annabella Meech and I'm a postdoc fellow at the CFA. And today I want to switch gears a little bit, bring us back down to ground and present some ongoing work that we're doing to assess the impacts of stellar inhomogeneities on high-resolution transmission spectroscopy. And just for the purposes of confining this a little bit, I'm going to be focusing on M-dwarfs in the near-infrared in this talk. So we've been hearing about how stars are not homogeneous. I'm preaching to the choir here. There's plenty of phenomena going on, and there's more than these. I've just listed a couple of examples. These can be roughly divided into two categories: things that are in transit-induced and things that are intrinsic to the star, i.e. things that occur because the planet is transiting the star, or things that occur no matter if the planet is there or not. And obviously the phenomena can be shared between the two categories, but it's the latter that I want to focus on today. And I know that we have a mixed audience in terms of expertise, which is great. So I just really want to quickly recap the technique of high-resolution transmission spectroscopy. If you're already aware, then please bear with me for a minute. How do we observe an exoplanet atmosphere at high resolution? We make use of the fact that the planet is orbiting its host star, and as it does so, its spectrum Doppler shifts relative to the other spectral contributions, i.e. the tellurics and the stellar spectrum. So over time, the planet traces out this nice sinusoidal curve. In reality, it doesn't look anything like that. The stellar contributions and the telluric contributions dominate, and once we've removed them, the job is then to try and bring out the planet signal from underneath the noise. The way that we do that is by forward modeling what we think the planet atmosphere contains, and then shifting that forward model across the data for a range of velocity solutions, obtaining a cross-correlation function. If we do that for every frame in our time series, we obtain a time series of cross-correlation functions, and we then collapse this in time by assuming some velocity. And if we do that for several different velocity solutions, we end up with a KPV sysmap, or as Mike Klein likes to call it, a blob plot. So each color here is representing a peak correlation for each velocity solution. But the key point for the purposes of this talk is that we assume the stellar spectrum to be constant in wavelength, not shifting, and in time pretty much. We wanted to examine what is the impact of that assumption. So to that end, we built a forward model, and this is very similar to other setups that have been described this week and some of the ones that Megan introduced us to yesterday. The basic premise is that we have a stellar disk, which is divided into a grid, and each point in the grid is assigned either a line profile or a stellar spectrum. We then introduce our transiting planet, around which we host an atmosphere, and this atmosphere is computed offline, where each stellar cell is the opacity from each stellar cell affected by the planet is recomputed. So for the work that I'm showing today, this is the model setup that I used. For the spectra, I took 1D BT settle models for the photosphere, and for the spots, cooler BT settle models. So Ben's comment on model fidelity is music to my ears. And then we have, for the planet atmosphere that we're looking for, a hydrogen-helium dominated atmosphere around a sub-Neptune containing water. And then I've concentrated on the cry-res bandpass in the near-infrared with cry-res resolution and a signal-to-noise that means that we're meeting the 5 sigma threshold level that is normally considered to be the threshold above which we consider a detection at high resolution. So I have been looking at a series of M-dwarfs from M0 to M9. Here is a family portrait. And for the spot properties, we adopted those from Ben Rackham's 2018 paper that they derived. And they derived filling fractions that differed between if they assumed giant spots or solar-like spots. So for the giant spot cases, they derived between 2 and 3% coverage fractions. And for the solar-like, between 30 to 50%, so significantly higher. So we've already seen this plot in Ben's talk. And this is just what we see at low resolution for unocculted spots when we assume solar-like spot coverages. And I guess the thing that I want to draw your attention to, they've noted some of the important band heads for some of the important molecules that we might be looking for in planetary atmospheres. And since we're looking for water in this talk, we see that for the M5 case, the water contamination contribution is higher than for the other stellar types. So for each of our simulations, we have some reference model, i.e. a spotless star, and then we have the spot case, where first we're just considering unocculted spots, and in each case we have that water atmosphere around the planet. What might we expect for unocculted? Oh, sorry. So we proceed all the way through to our blob plots, and then we compare the signal to noise in both cases. So for high resolution, we again have a difference between the stellar spectrum out of transit compared to in transit, because you're blocking some contribution from the photosphere. What did we find? Firstly, for giant spots, on the x-axis I'm showing the stellar type tested, and on the y-axis, the signal to noise of the water detection from the spot case compared to that spotless case as a percentage. So the thing to note on the y-axis is that a positive percentage is meaning that we're inflating that water detection when we include spots. So for these giant spot cases, i.e. coverage fractions between 2 and 3%, we found that the signal-to-noise difference was tiny, probably not distinguishable between that of the star and the planet atmosphere. But that wasn't the case when we increased the filling fraction. So when we go to the solar-like spot cases, we were seeing up to a 10% difference in the recovered signal-to-noise. And again, this matched the predictions from low-res, where the contamination was higher for the M5 case compared to the other earlier and later equivalents. So we wanted to narrow down into one particular user case, and that was AU-MIC, and we varied the spot parameters. So the y-axis has stayed the same here, but on the x-axis now we've got the temperature contrast used between the photosphere and the spots. And in each of the 3 panels, we've assumed a different filling fraction according to those given in literature. So the first thing to point out is that for the 5% coverages over there, for these low filling fractions, we're not seeing a significant increase in the water detection when you include spots. But as you increase the filling fractions over to the left, 40% coverage, you can see up to a 35% difference in the signal to noise. And this also increases as you increase the difference between the photospheric temperature and the spot temperature, as we might expect, since it's the residual between the two that we care about. So we think that this is going to be important for detections that are marginal on the edge of being significant, where you might not be able to conclusively say that your water detection is from the atmosphere rather than being a little bit boosted by the presence of unocculted spots. So moving on then to occulted spots. Again, we have our reference case, which is spotless, and now we just include spots along the transit chord. And we introduce a new parameter, which is the fraction of the transit chord covered by spots, rather than a total filling fraction. Now we might expect the opposite. So in transit, we're obscuring some contribution from the spot spectrum rather than the photosphere. What did we find? So here I'm showing an example of the M4 stellar type. The y-axis is unchanged, while the x-axis is showing the fraction of the transit chord covered by spots, increasing as we go towards the right. But now notice that the y-axis has changed to being negative, i.e., as we increase the number of spots along the transit chord, actually we're decreasing the detection significance of a water atmosphere. We also tested this as we also saw that there was a temperature dependence on this fall-off. So for different stellar types, we found that this tailed off more quickly or less quickly. So I'm just about coming to time. Some of the takeaways from the tests that we've done so far show that unocculted spots may artificially increase your cross-correlation detection significance with high-resolution cross-correlation spectroscopy. But this is only for very high filling factors. And at the low filling factors that are important for low res, we might not have that distinction. We might be less sensitive to the unocculted spots. The reverse is true for the occulted spots, where this can potentially decrease the significance if the spots contain species that you're looking for in the planet atmosphere. So thank you very much, and I will take any questions.
Great, thank you. Question?
Hi, Annabella. Cool work.
Hi.
I'm curious, so you talked mostly about just detection significances themselves. Have you looked a bit into, like, if you couple this with, like, a log likelihood framework, how that affects retrieved abundances of water or stuff like that, or have you mostly just focused on, like, the straight detection?
Yeah, you're completely right. So we've just focused on the signal-to-noise metric for these tests, but I do expect that it would have the same influence on retrievals. When it comes to actually trying to correct for this in retrievals, I think we're a long way off, given everything that Ben presented on model fidelity. We really need more accurate stellar models if we're going to try and forward model this kind of effect.
Thank you, Mel. This was a really nice talk. Have you thought about doing this for a distribution of spot contrast and distribution of spot sizes? And then also sort of related, what spectrum did you use for the spots versus this non-spotted part?
So we've been taking cooler photospheric models for the spots, which we know is an inaccurate assumption, right? But that's kind of the best that we're at so far. And the reason that I've used the 1D models is because we want to explore a wider range of parameter space, and the 3D models are just not available yet. Although there is ongoing work to, as Ben described, to try and get accurate spot and factly models. And I'd point to Rosa's poster if you haven't already seen it. And sorry, what was your first question?
Distribution.
Oh, yes. So in terms of distribution over the disk, or?
No, like there's a distribution of temperatures, distribution of contrast.
So yeah, we have investigated distribution in spot in temperature contrast, and we see that as you increase that contrast, then there's a worse effect. But there's going to be a tail off where your spots start to become opaque and then have less spectral contribution. In terms of distribution over the disk, I don't think that matters so much because it's the total sum that we're looking at rather than position. Actually saying that, though, we are next going to be trying to investigate if spots concentrated on the limbs actually have a more minor effect than concentration on the center. Yeah.
Thanks.
And then one more down here.
Sorry if I missed this before, but, oh, by the way, sorry, I haven't been introducing myself. I'm Dom from the University of New Mexico. So you were expressing everything as a percentage change of SNR, but did you mention at some point what, like, the baseline signal-to-noise threshold was to begin with?
Yeah, so they're all above 5 sigma, which is what we normally take to be statistically significant at high resolution.
Gotcha. Okay, thank you.
Perfect. All right, let's thank our speaker again.
Thank you.
Thank you.